Well, students, today it's time for lesson 4.3, day one. Does caffeine increase pulse rate? Let's take a look. Mrs. Gallus and her students decided to perform the caffeine experiment. In their experiment, 10 student volunteers were randomly assigned to drink cola with caffeine, and the remaining 10 students were assigned to drink caffeine-free cola. Were their findings statistically significant? The table shows the change in pulse rate for each student, final pulse rate minus initial pulse rate, along with the mean change for each group. So we have all these students, and they figured out their change. They took their pulse rates before they consumed any cola whatsoever. Then they took their pulse rates after they consumed their cola, and they recorded the results. These are the results for the students that drank the caffeine. The difference between, this is basically the amount that their pulse rate went up from the first test if they had done or drank the caffeine. If they did not drink the caffeine, if they drank the caffeine-free, then this was the results. So you can see that there was a mean of 3.2 and a mean of 2.0 that we're going to subtract to get a 1.2 difference. It says find the difference in mean pulse rate for the groups. Does your initial reaction lead you to believe that they found evidence that caffeine does or does not increase heart rate? And explain. So when you subtract them, you get a 1.2 difference. It is possible that the caffeine caused an increase in heart rate, but a difference of 1.2 does not seem real significant. It may have happened by chance or other factors. Question 2, what are 2 possible explanations for the difference in mean pulse rate? One is that caffeine actually caused the change. Another is that it was just a coincidence by chance. All right, at the end of this note page 1, they would like us to do one of these samples in class, which we're not going to be doing for this video. Then they would ask us to find the mean change for each of our students, subtracting and figuring out the mean difference. Then we would add our difference to a dot plot. We would do a simulation and we'd do a dot plot. This is just going with that 1.2 that they had. So you would do a simulation, you'd have all these dots of all the simulation. If you just did it by chance, could it be a 1.2 difference or more if there was no caffeine effect whatsoever? And in our book, when they did this, it turned out to be 19% or so that were above this number. So that was not going to let us say that our results were statistically significant. The difference in means, what does each dot represent? So each dot would represent the difference in means of one trial, the caffeine group mean minus the non-caffeine group mean. What percentage of the dots are greater than or equal to the difference in means of 1.2 found in Mrs. Gallus's experiment? So we would add our dot to whatever this is, the dot chart. But when she conducted the experiment, they did the simulation, 19% or higher. So then interpret the percentage. Assuming that caffeine has no effect on heart rate, there is a blank percentage, which we'd have to figure out after we do our own simulation. Probability of getting a difference of 1.2 or more purely by chance. In this case, it was, from the book, it was 19%. So then how do we decide that was not statistically significant? Well, your book suggests we use the 5% rule. If the percentage is less than or equal to 5%, then our study is statistically significant and our result is probably due to the caffeine. However, if the percentage is greater than 5%, which it was for Mrs. Gallus's class, then the results of our study is not statistically significant. It may be a coincidence by chance. Let's take a look at your notes. These are your notes for section 4.3, day 1. Inference for experiments. All right, so your big ideas. You got a couple big ideas here. So sampling variability is the different samples yield different estimates. So if you were to take a whole bunch of different samples, each one is going to have a slightly different mean. They're probably not going to have the same exact mean. It's possible that they would, but that's sampling variability. So if you chose, like for example, in that football player example that they had in the book, you chose 50 NFL players and you got a mean weight, average weight. Now, if you were to do the test again and randomly select 50 NFL players and do the weight again, the chances are very likely that you're not going to get the same mean. And that's just the way that it works mathematically. So don't be alarmed. And chances are you could conduct several of these samples and not actually get the true mean of the group. But what you're looking for is to try to get close to the mean. So that's why you do the experiments or the tests. So larger samples produce more accurate estimates. The more that you have in your sample, the better. So for the football player one, if you have more than 50 people that you're selecting randomly, you're probably going to get a little bit more accurate results. Let's say you chose 100 or 200 players. The more that you select, the more accurate your results theoretically are going to be. Question B, if another random sample of 50 NFL players was taken, actually, I think I missed the rest of your note section here. Statistically significant. Let's see, margin of error. Let's talk about margin of error. It creates an interval of plausible values, a range of the sample estimate plus or minus a margin of error. So that they'll give you a range, and then you would say it's plausible if your mean fell within that range. And if your mean did not, it's not plausible. So then you might have a statistically significant situation. So statistically significant means when the results from a study are too unusual to have occurred purely by chance. So in order to figure that out, you have to conduct simulations. In fact, you wouldn't conduct just one simulation, you'd conduct many, and you'd probably use electronics to do that. And then these dots would represent all your simulated trials. Then this was your sample, which would have been like the 1.2 for Mrs. Gallus's class. If we had less than 5%, less than or equal to 5% of the dots on the right side, then we would say that's statistically significant. If the number of dots on the right side of our line are higher than 5% of the total number of dots, we would say that it is not statistically significant. So moving on to this NFL football player one, you've got 244.4 pounds is the average weight that they found in this sample of 50 NFL players. Now it says, do you expect that would happen, or do you expect that would be the true average of the NFL players? And no, we don't. It's a sample. We know that our sample is not going to be the exact average. It is possible. Anything's possible. We may have hit one that just happens to give us the exact average, but it's likely that it's not the exact average. It's just an approximation. Part B, if another random sample of 50 NFL players was taken, do you expect the average weight to be exactly 244.4 pounds? No, we'd expect it to be different. We'd expect that samples to be different. Now, there might be some samples that are the same because there's a possibility that could happen, but we expect them to have some kind of variation and difference. Part C, estimates are usually given with margin of error. The margin of error for the estimate of 244.4 pounds is 14.2 pounds. Based on this, would you be surprised if the true average weight of NFL players was 260 pounds? Well, let's check the range for plausibility. So it said the margin of error was, what did it say, 14.2. So here we go. We got 244.4 was our average. If we add 14.2 to that, we get 258.6. 260 is beyond that. It's outside the margin of error. So yeah, we would be surprised about that. Part D, which would be more likely to give an estimate close to the true average weight of all NFL players, a random sample of 50 or a random sample of 100? Well, The bigger the better when it comes to samples. So we would say that the random sample of 100 would give us the better estimate. Larger samples produce more accurate estimates. That concludes our notes for today. Once again, we want to thank our friends at Stats Medic for providing us notes that coincide with our textbook. So this is your math teacher, Mr. Murphy, signing off for today. Stay awesome, Spartans.